All right. Yes. Okay, so data file formats is the topic of my presentation. It's a topic that I chose because it's usually relevant to data engineering, BI work, especially in the became much more relevant in the last few years with the advent of lakehouse technologies, data lake technologies, things like that. And we're moving more from a relational database world or analytical database world to file-based analytical setups. And that's where data file formats come in, of course, and that's what I'm going to discuss about today. Let me check whether my laser works correctly. Switch slides. Yeah, okay, now I got it. So I'll start with, of course, the introduction, a bit of definitions, because the topic of data file formats can veer quite into the territory of computer science. So some definitions to start off with and to get everyone on the same page is always useful. The thing that I'm going to spend the most time on actually is the features, and not tying them yet to a certain data file format, but just discussing features that make data file formats fit and useful for data engineering and analytical purposes. So I will go deep into the different features that data file format may or may not have, as we'll see later. And after that, tie it all actually taking a look at some of the most used data file formats in data engineering today. So first, for these definitions, let's start with a very basic definition. So what is this data file or file format in general? So file format, or should I say a data file, is a computer file in general, which stores data to be used by a computer application or system. So it stores data and not code, which is an important distinction, because a data file is used by a certain program or in a certain context and to do useful things with it. We all know it. Examples like JPEG or an MP4, things like we've all used are all examples of file formats. And a data file, while it may be used interchangeably, is actually an instance mostly of a file format. So if it makes sense, a data file is like the file that you save on your computer, and a file format is like the extension after the dot, which offers certain features and identifies it to be used with a certain program. Now, of course, this is a topic about data, about analytics, and about data engineering. So data file format is not really a term that's strictly defined. I try to define it myself. Sometimes you also hear about big data file formats because of the hype around the word big data of a couple of years back. So this is how I define it. It's a file format, anyone that stores structured and or semi-structured data used for analytical and data engineering workloads and purposes. And these file formats offer purpose-built features to aid in this specific goal. So this is more like an academic definition, but to make it even less abstract is how do we store tables and or data for analytical purposes with these file formats. So here is a quick overview of all the features that I'm going to discuss today. These are features that a certain data file format may or may not. I'm looking at these features in general, discuss how they work, discuss why they can be useful or why they may not be useful, and such that you know how they work. People who have done a lot of database development, relational database development, will also recognize a lot of these features as being reminiscent of features offered by databases. And that is, of course, because these are closely interrelated. Of course, database is also just a way to store data using blocks mostly with a lot of features on top. File formats have converged more to features for analytical purposes, and that's why these two are often interrelated and may be relevant to both databases and file formats. So the first feature that data file formats may have is one that's already taken from the relational database world, and this is column typing. So if we have a table that we want to store and it has certain columns containing data, it's often very useful to give a column a certain data type. For example, if you only want to store integers in there or decimals, things for calculations, you give the column where you want to store these the integer data type or decimal or float, whatever you want to call it. There are often different names. Dependent on which framework, software, or programming language you're using. Date type is another one, and of course, yeah, string or object or varchar if you're in varchar if you're from the SQL Server world, is of course just a column where anything goes basically, but it's often not the most specialized. It's usually better to, if you know that you're going to store integers, decimals, or things like a date or a date time in a column. It's usually better to use that those data types instead, because of course most people who have worked with or who have done some data engineering work or done some database development work know about people storing all kinds of data in varchar max columns. I'm talking about SQL Server because most of us work in a Microsoft BI world, which is fine because you can put everything in there, but it's often not optimal. And why it's not optimal depends on two reasons. First, if you do your column typing correctly, if you give the columns where you will store the data the correct type, this can be your first line of defense against the data quality issues. For example, if you store an invalid date in a datetime column, it will often be rejected, or at least you can flag it, depending on what you want to do with it. And this is already a first enforcement of data quality, which can be useful. Also important, if you want to store numbers there and you give it an integer, you make sure it is compatible with the calculations that you want to do with it. If you store, for example, a string, you can store text there and you can do contains operations or like operations to look up values that contain a certain string, that match a certain string. Giving the correct data type to your columns can also improve the performance of queries and analytical processing that you do with the files, because your query optimizer can make certain assumptions. If you, for example, do use calculation functions on a column, and it knows that all the values in the column are integers, it knows how to proceed, and that it does not have to check for any non-valid integers or non-valid numbers or decimals mostly. And the size of columns on disk, that is when it's stored and addressed, is also affected by data type choice. And this is also important because input-output I/O operations are a huge part of performance when doing queries. So if you have smaller columns is better, and integers, for example, and decimals are much more are smaller to store than strings, and that's also affects query performance. So on the one hand, we have the data quality issues that, or data quality that can be enforced by doing correct column typing. Otherwise, column typing also impacts size on disk and, of course, query performance, because less bytes have to be read in memory when executing certain queries. Another huge distinguishing feature between data file formats or analytical databases and relational databases is whether you store the files and the data in the tables that you have in a columnar format or in a row-based format. And what this actually means, we hear this a lot. For example, Power BI uses columnar storage. This is and SQL Server uses row-based storage. And this is actually talks about how the data from certain columns are grouped on disk. So in a row-based storage format, all the contiguous values for a row are stored next to each other on disk. So you can look up full rows quickly. And in the columnar format, all the values belonging to the same column are next to each other. So it stores columns values contiguously close to each other. And if it has to piece together rows, then has to go look in multiple places if it's columnar to piece together the values that you need. So the question that you have to ask yourself when deciding upon whether you want to use row-based storage or columnar storage is what's your workload access more, basically. Is it more like full rows that it will access, or at least big parts of rows that it might be more advantageous to use row-based storage? If you mostly work with column values or aggregations, which is more relevant for analytical workloads, then a columnar storage is often more useful. This harkens also back to the days of like more transactional application workloads who quickly create, read, update, and delete certain rows, or more analytical processing, for example, selecting only certain columns to do analysis on, aggregating them, partitioning them along the columns. Then you want to use more of a columnar storage-based format. One of the big ones, of course, or you prefer small ones, is how large or small are my files when stored on disk. This is especially important in the time of runaway cloud costs and cost optimization when using cloud storage. So how highly compressed can you highly compress your data? And there are certain techniques for compressing data files that I will look more in depth at, because I think everyone knows that you can compress files, but to make it less abstract, I want to outline some techniques that are used for compressing files. So the first one, if you want to compress your columns, this is one that's relevant to integer or number columns, is value encoding. And with this algorithm, you actually look at the lowest value of a column, the lowest number value. In this case, it's the 3004, the first one that I noted here. And if you found this minimum value, the algorithm subtracts the minimum value from all the numbers in a column, so making them smaller. So here you have the lowest value is 3004. Then from all the other values in the column, it's going to subtract this 3004 number. And the result will actually be stored, especially with the decompression key, so at 3004. It will store that information, and you will actually have a column on disk with much smaller numbers. And I said the smaller data takes up less bytes, or bits in this case, because it's even these are very small integers. So it optimizes for the size on disk, it compresses that, and this is one technique used for compressing number columns and highly useful. Another optimization that is done on non-integers is hash encoding, or dictionary encoding is another term that's used for that. So with this algorithm, the optimizer or the compression algorithm is going to look at values that are not unique. We see here product 1, product 1, product 1, and then you have 3 rows with product 2, 3 rows with product 3. And it's going to give each value in a column. If there are multiple instances of a value, it's going to give it's going to construct a dictionary or a hash table, whatever you want to call it, and give each value that's actually the value of the column that you want to access is going to give it an ID. And on disk, it's going to store it then using the row number and the ID that can be looked up in the hash dictionary that's stored along with it. So the end result is we move from the first column here on the left on the slide, and we store on disk actually the encoding dictionary and the result set with the row number and just the ID. So if you want to decompress this, then it becomes very simple because you have a much smaller column here, and when you want to decompress it, you can look up for the row numbers 1, 2, and 3. The ID is 0. Then you go to the hash dictionary and look up which value corresponds to the 0 ID. That's product 1, and that's the way that you reconstruct it from disk back into memory, and vice versa. If you want to compress it, you store it from a memory or from a file back into disk using the hash table. There's also see the red line here is of course that you see that the stored column on disk is much smaller because storing these hash table values 0, 0, 0, of course smaller than storing the string product 1 or product 2. So that is another optimization that is done. And then run length encoding is also a very interesting one. Here, this is also used for a large table and can be used for strings and integers as well. And in this optimization or this compression technique, the optimizer is going to look for values that are contiguously the same values in a column. So again, I have here the row number on the left picture on the slides. You see 1, 2, 3, all the way up until 363 contain the salesperson ID employee 1017. So it's from 1 to 363 all the way across all these rows. It's the same values. So the employee 1017, and the same thing goes for the next value. So employee 1043 also has rows for starting from 364 up until 727. So what is the compression algorithm going to do? It's going to look where, and the name already gives it away, run length encoding, for how long does the same value occur contiguously. Taking the first example, we have 363 rows with employee 1017. It's then going to construct a smaller, more summarized table where it stores the value, the actual column value, so the employee number here, and it's going to record the row start and the row end values, as well as how many repeating values there are. As we can see, if this is done correctly, you can see that the end result table only has 3 rows and with 4 columns, while the original column that is compressed under the form of this table has more than 1,000 rows. So it's not always that the values are contiguously or that it's optimal to do this, but if it works, it can offer huge benefits in compression and thus size on disk. So and the key listener will also recognize these optimizations as the optimizations from the Power BI Vertipath engine. These are all techniques that Power BI uses when storing data after loading it into memory. But these are also generally used compression techniques, and that's why I want to outline them, because that way you have more of an idea, if you don't have a background in computer science, of what an algorithm or what a program does when it stores files on disk and how it gets that much smaller. That is because of some of these optimization techniques. Important, the compression affects read speed, because as we saw with all these optimization techniques, the end result that's actually stored on disk is of course different according to the algorithm used than the original column. And that's why it affects read speed, because it has to reconstruct these columns from the way that you stored them on disks. So harkening back to this example of the run length encoding, this table on the right is what's stored on disks. Now, if you want to load this into memory to actually do something with it, query it, or transport it, or pass it on to another process, it of course has to reconstruct the original column from the table that you stored on disk. And if that's done, if you have chosen an inefficient compression algorithm for the column that you're using, this can actually take quite a long time, so that's something that keep in mind. Compressing files is nice, of course, and a smaller file size is usually better, especially when you're working with cloud-based storage, because then you get built less. But it also affects read speeds and, of course, write speed as well. The same is true for writing files from memory to disk, because it has, of course, to apply all these optimization algorithms before it gets written to disk. So this, of course, takes some CPU cycles as well to do. All these optimizations and compression techniques take up computing time, and that's why it's all these encoding and compression techniques also affect write speeds, of course. Now, write speeds are usually less relevant for analytical purposes. However, not completely. If you're thinking, for example, about streaming data sets or streaming rows to your disk, the write speed may be a factor to make sure that things don't get blocked up during the process, or when things have to, when your writing process has to reorder partitions, which is something that we'll talk about in a minute. Then write speed can also be a factor, especially if for applications like Internet of Things applications, where speed is of the essence, where you want your rows available as fast as possible on disk. So compression, size on disk, very important, but there are of course some trade-offs as with computer science. And read and write speeds, I already talked about it just now. We talked about compression. So basically, yeah, how fast does it take to read my file from disk into memory, which is important for analytical purposes, especially as you're working with bigger and bigger data sets, sometimes running millions or billions. Yeah, and read speed, of course, becomes very important because you don't want your business users to be waiting hours to answer a simple query or a complex query. But in that case, it becomes a case of query optimization. But that's not the topic of today's presentation. So this is also a feature that's important when evaluating data file formats. For analytical purposes, it's mostly important to see how much time does it take to read the data from the file. Writing data to a file, also relevant, but that I already talked about when using compression. And in general, as I say here, read speed is more important for analytical purposes. Write speed is not always negligible. But mostly you want to look at read speeds, especially because mostly you're going to be doing querying, aggregating, and the writing processes will be done more in batches, so it has more time to write things in the data to disk. But all these things are interrelated, as I already touched upon in the compression technique section. So read and write speeds, size on disk are all affected by encoding, and there are all trade-offs between optimizing for read speed, for write speed, and for size on disk. So take that into account, as always, when choosing a data file format. Take into account your requirements, take into account what's important to your end users, so you can make an optimal choice based on what you know about the data. Okay, another feature, and this is a big one. It's mostly a distinguishing feature that makes it so that CSV is still widely used. We'll talk about CSV in a minute. And that is whether the file is human readable, whether it's a text file with ASCII characters that can be opened in a text editor like Notepad or Vim and be interpreted by humans, which of course makes it hugely useful if people can just click open a text file with any text editor and inspect the data inside. That makes it a hugely useful feature. And the other category is binary files. And binary files are files that are stored on disk the same way as they are laid out in a computer. So in the binary form, that's where the name comes from. And this is often more efficient for computers because computers can read in binary files much more quickly. And also, a lot of features can be added to binary file formats that are often meant to be used with certain programs, programming languages, or frameworks. So if you construct a binary file format for a certain program, that is often much more optimal for computing, but of course, less for humans. So that is why you have to think about what you want to do with the files, where it's going to be used, which software you're going to use with it, and then you can make a decision based upon whether you want human readable files, which are the text files, and binary files that contain the data as it is laid out. For data engineering per se, and ETL, batch processes, flows, mostly you're going to be working with binary files because mostly after the code is pushed to production, your pipelines are in production, only the end result matters for analysis, but the product in between, the files in between, are meant for or pipelines or computing frameworks will be working with them. For example, things like Azure Data Factory or Python or Airflow are all ETL frameworks that work best with binary files because they use that to read in metadata, and it's more efficient for them to read in binary files. And again, to make this less abstract, I have here I have inspected a JSON file and a Parquet file with the same context, with a file editor that can open both. And the JSON file, the people.json file at the top, it's very much human readable. You can see here that the first person is named Michael, and the second person is named Andy, and he's age 30, and so on. So a person can open this on his or her computer, have a look at what the data contains. It's maybe not optimal, but JSON is still very much readable for a human, which of course isn't the case for a file containing exactly the same data called people.parquet. So it's mostly gibberish unless you know what to look for, but this is clear that it's meant for opening with specialized software or specialized programming languages. Python can open that, of course, with PySpark and with Pandas. And then the people.parquet file will be rendered, if read incorrectly, as a table. But this is just to hammer home the difference between human readable files and binary files. So we will be talking that when we have a look at the specific file formats. A last feature for file formats, or not the last feature, but the last feature before we tie it all together, is partitioning. Partitioning is where you delineate different chunks of data in a table based on a key. And what do I mean by that? If you have, for example, a table containing purchase orders, and every day, nightly, the new purchase orders from the day before are read in, you can actually partition the end results table with containing all the purchase orders for a certain period of time based on the date column in this case. So that way, we will see it when we talk about predicate pushdown after this. If we partition it on date, a process reading in the files, the files, because you can partition between files also, and you only want certain dates, it knows where to look and it doesn't have to read in all the data, which is of course optimal, because as I said, input and output processes take the most time in doing analytical workloads. So you can partition inside of one file. If you have, for example, one table stored as a Parquet, you can, of course, partition along the date. But it's also often useful to partition between files. I'm harking back to this example of a table or an ETL processing, writing the purchase orders that were made the day before to disk. If it writes a new Parquet file every time in a folder in a data lake, for example, on Azure Data Lake Store, it creates a new folder, it creates a new Parquet file, but you can still tell the process, for example, Spark or Synapse reading Synapse serverless, reading in all these files as one table, the purchase order table, that it is partitioned along the date column, and the process that is then going to be reading in the different files to construct one table, to render it as one table for analysis, will be able to do some query optimizations and only pick up the files that need to be read to satisfy the query. So partitioning sounds great, it is great, but you also have to think about which column you choose to partition on, because inefficient partitioning can hurt query performance. What I mean by this is that if you take a partitioning column and end results or the resulting files are way too small, you can incur actually a lot of overheads for reading in all these small files to construct one table from it. This is, if you, for example, have IoT processes where, because that's the quintessential example for big data, so I take it to illustrate extreme cases. If you have IoT sensors, multiple IoT sensors writing a batch of observations every minute, and you partition along this minute, and you want to aggregate this data, for example, for a couple of months, then it's going to have to read from all these sensors and all the files in for every minute, which is of course going to be a lot of files if you want to look at some data from multiple months. And that is then inefficiently partitioned because the process reading it in will incur a lot of time, overheads, and it will hurt query performance because it has to look at small file, add it to the result set in memory, And that's why it will take a longer time if you inefficiently partition files. Still, sounds obvious that you want to partition. It's mostly useful with very big data, think millions of rows. If you use, for example, Synapse, dedicated SQL pools, Microsoft has a lot of recommendations and a lot of guidelines on which columns to partition and which row, the size of your row groups that are optimal for the distributed nature of Synapse. So just to summarize, read up well on your framework that you will be using to read in the files, the partition files. Think about the analysis that will be done on the files. So you can choose a partitioning column that is optimal for query performance for this analysis. And then you can choose a correct partitioning strategy for the files. Not a last feature, also I'm looking forward to talking about predicate pushdown, which ties it all together. But first we have to talk about statistics and metadata. Is that files on disk can contain certain metadata and statistics about the data. And what do you think about when we talk about that? For example, it can store for integer columns the minimum value, the maximum value. For strings repeating values, it can store the column distribution, but also things like column typing, like we talked about in the first feature, and construct a schema for the data. The process reading in the files know which type the columns are, what their names, how they should be constructed. And this is also useful. These statistics are useful for query optimization because the process reading in the data can make certain assumptions. If, for example, knows the minimum and maximum value, it can reject values or filters that are out of bounds. If you have push, for example, a filter in your query on an integer column that is, and the filter is higher than the maximum value, the query optimizer will look at the maximum value and will already know, based on that information, that there is not a value in that column satisfies the query requirements. We can give you a results very fast without checking all the rows and all the values in that column, whether there is actually a value that's or a cell, so to say, that satisfies the query. And this is also very reminiscent or is very closely related to the statistics and the metadata use that are used by query optimizers in relational databases. All the DBAs and all the people that have done some SQL Server development or any relational database management or administration will know that up-to-date statistics for your tables and up-to-date metadata for your tables are very important for the query optimizer to construct a good query plan. And if you have outdated statistics, which can happen over time as you write more data to a file, then the query optimizer will not be able to propose a query plan for your to satisfy your query as good as it can when the statistics are up to date. So it's great to have it. Still important to keep it up to date. Luckily, lots of features are offered by data storage and data processing frameworks to update these statistics automatically. For example, I talked about Synapse dedicated SQL pool already. It has some flags that you can set and to update statistics automatically, which is useful because if you have nightly ETL processes that write data to a file, and you have the flag set on to, after the ETL process, update the statistics, then your business users will wake up and get to their computers with up-to-date statistics, improving query performance. So we talked about the partitioning, the statistics, and the metadata, read and write speed also. So now we're going to do see how it all ties together when doing some analysis. So predicate pushdown is a fancy word that harkens back to relational database, relational algebra, but it basically means if a user asks a question from the data, as we see in the query here in the middle, here it selects user IDs that are bigger than 200. Is it possible for the framework that you're using and the storage file format that you're using to push the query selection to the file format. So we only have to read in data rows or columns that satisfy the query requirement. And for that, let me first walk through the example, because that's going to make things less abstract, as I like to say. So we have here the Parquet, our 3 Parquet files rather, just generically named file part 1, file part 2, file part 3. And the first file contains a minimum value of 0 for the user ID and a max value of 100. 101 for the second file as a minimum value, the max value is 200, and 201 for the third file, and 300 as a max value. So this is where the metadata comes in, because it stores these min and max values along with the files for user ID column in the metadata. And when then the user executes the query that we have here, this very simple query where it wants to filter on only the rows where the user ID is, or yeah, only the rows, only the column user ID where the user ID is bigger than 200. If these statistics are included along with the file format, and the statistics are up to date, of course, the processing framework takes Spark or Synapse serverless tools, will be able to look at the metadata and will be able to push this predicate or this filter in this case down to the file and only reading the rows from file part 3, because looking at the metadata, it sees here that the minimum value is here 201 and the maximum value is 300. So the rows in this file will satisfy the query. And rows in the file 1 and file 2 obviously won't, because these have user IDs that are 200 or smaller. And this is very useful because reading in less data, it's a recurring topic, incurs less I/O time. And this way, not the full file or all the files do not have to be read into memory to then inspect the column values to actually see which values satisfy the query predicate or the filter, to use a less fancy word. All right, so these were all the features in general. I have already talked about, or I have already mentioned things like Parquet, CSV, things like that. And now we're going to have a look at the data file formats for themselves and have a look at what they're useful for, how they work under the hood, and things like that. Okay, so the first format is our delimiter separated values. And these are just text files that use a delimiter, such as a tab or a semicolon, but most frequently a comma. A CSV file is the most ubiquitous one, and this is also this file format. The delimiter separated values is also the lowest common denominator of analysis formats, as I like to see it, because it's a CSV file. Almost all software can work with CSV. Your business users or everyone can open a CSV file in an editor and inspect the data inside. And I'm sorry, I was on the wrong slide. So here we have the delimiter, the different delimiters that can be used, so comma, tab, semicolon. I called it in general delimiter separated values, but you will recognize CSV, TSV, or SV, CV as more frequently occurring data file formats. And these are text files that are human readable. But there are some shortcomings with it, because any of the features that we discussed about, except human readability, this file format does not offer. It's also not standardized. So anyone can do their own text implementation and use different separators. And if you, for example, open a file, you expect it to be separated with commas, but it's separated with tabs. Of course, it won't render correctly. But despite all the shortcomings, it's actually indispensable because of it. It is so widely supported by data processing frameworks. It can be opened by anyone in a text editor to inspect the values inside. But you shouldn't use it to build out a data product. You shouldn't build out a data product fully using CSV, because then You will have complaints about, for example, slow read times or write times in no time, because things like metadata file formats or column types that are all not supported when working with delimiter separated values. So yeah, here most people know how this looks. This is just a CSV file opened in the in a text editor. It has no column headers, which is also an interesting point, because when you want to give the column headers, you also have to put that in as a first row, and you have to specify when reading in a CSV file. You have to specify with your process that you want to use the first row as column headers, which can be quite of a pain, because if you haven't inspected the data and there are no column headers, then of course it will take John Doe at 120 Jefferson Street as the column headers, which isn't of course correct, because that's a record already. So another difficulty we're working with the CSV files is, which row do I take as a header? Are all the data type correct? And that's why it's not that useful for intermediary data products. And the last thing that I want to talk about is this file is separated using commas. Now, what, for example, if you have a street name or a city name that contains a column, that contains a comma, it might happen. You have to escape this comma character in your column value to indicate to the processing framework or the software that you're using that it isn't actually a delimiter, but that is part of the column value, which can also lead to trouble when reading these CSV files. A second type of file formats that I want to talk about are what's fancily called serialization languages. I have a picture here of Json, which is the most widely used and also the most widely used in data engineering, but also in programming. When programming APIs, Json is used very frequently. But other examples of it are XML, which was used frequently in the past, and YAML, which is also a serialization language that is used, and that is more human readable than Json. Although I think if you know what to look for in a Json file, as you can see here, it's still quite readable. So these serialization languages are actually a form of semi-structured data. They are not in tabular formats, but rather they have a key and a value. They use a key and a value notation, or Json does at least, to look up data. For example, if you want to find out where your servers are, you look for the server's key, and then you can find out Chicago, New York, it repeats, and the description of the server you can look up by looking at the key desk here. And those are data centers in group A for the first record. The description for the second record is data centers in group B. These records are separated from each other using commas, and curly braces indicate the full record. A big advantage of the serialization language, and especially of Json, is that you can nest records. So you can, for example, have a key that opens a value, and then you can put in another record inside. If you want, for example, mark a first record with a date, with the person who created it, and then as a third record, you want to contain all the purchase orders that he or she created. You can open new curly braces and put in a new JSON record there to nest data. Makes it quite a pain to untangle, but luckily JSON is so widely supported that now things like even Power BI, T-SQL, Python, Pandas, Spark, all offer support for untangling nested JSONs, which and fit it neatly into a table, so that it's easy to work with when doing data engineering. I mentioned APIs because JSON originally harkened back to JavaScript, although it's now so widely accepted and widely used that almost all programming languages offer a way to work with JSON. But often APIs, when calling APIs, which is also often done in data engineering, the resulting data will be in JSON. And it's up to the data engineer to untangle, to look at the structure and the schema of the JSON file and untangle it based on the requirements. I've done that quite a lot, and it can take some time getting used to, but once you know And once you get the hang of it, it's actually a very useful format to receive, because you can just also pick up the records and the data and the values that you want and discard the rest when doing ETL processes. The next data file format is Parquet, which is, as I mentioned here on the slides, the golden standard for data engineering. These are my words, of course. I like Parquet very much, and I think a lot of other people who have done data engineering in ETL or worked with data lakes, file-based formats, analytical frameworks will like Parquet a lot, because Parquet offers almost all features that we discussed about in the first section. It has your statistics and metadata about the data inside. It compresses very, very well. It offers very fast read and write. I have a timed example of it compared to a CSV on the next slide, and you will see that the improvements in read and write times are very impressive when compared to CSV files containing the same data. It has only been, the first version of Parquet was released in 2013, the first standardized version. Before that, it was in beta. But it has become so widely accepted because of its usefulness that it actually has pushed out comparable file formats such as ORC, which is mostly used by Hive, Apache Hive. But that's why I dare to say that Parquet is now the golden standard for data engineering, especially because things like storage frameworks such as Delta Lake and uses it as a standard. Apache Iceberg can also work with Parquet files. So that means, Delta Lake, that's Databricks, and also now Synapse. So it is a very efficient file format in and of itself, but it also offers further optimizations when you work with a Delta Lake structure. And things like that. So here I have a comparison, a nicely laid out comparison from a Canadian care provider. And these guys went to work on a 16-core machine with 1 terabyte of RAM, running Ubuntu, Linux distribution. And they fired off some queries on a CSV file containing the data and a Parquet file containing exactly the same data. They wanted to see whether the size of the data set mattered. So we have a very small data set, a small measured in number of rows, a medium, and a large one. So the large one has actually 408 million rows. The small one has only 370,000 rows. Columns are comparable, 200 columns, so a very wide table. And the first table looks at the file size differences. And I take the large one because the optimizations made by Parquet are the most prominent there, or the most eye-popping, so to say. So the CSV file containing these 408 million rows was 351 gigabytes in size, and it was only when stored in a Parquet format, it was 45 gigabytes in size. So we have an 87% decrease in size on disk, which again matters for your cloud costs and your storage costs. And this was across the board. The decrease in size. Is there a question or?
No, Peter, sorry. We have another 5 minutes because then in 10 minutes we have another session. So,
of course.
Okay, thank you. Thank you.
So the decrease in size is quite sizable. I'm going to move faster through it then. And the processing time for reading in a complex query, they grouped by dimension and 3 columns and calculated the minimum, average, and maximum of a numerical field. We saw almost a 99% decrease in processing time due to the predicate pushdown and the statistics and the metadata that Parquet offered, while the large CSV file even gave an out-of-memory error because it was too large to read. So huge optimizations by using Parquet, and that's why it's also the file format that's most useful for data engineering. The last one and the last slide that I want to look at is the Apache Avoc file format, which offers a lot of the same optimization and features that we discussed about in Parquet also offered. But it is row-based, and that means that it's optimized for writing and makes it very optimal for streaming data, because streaming data continuously writes records to disk. But it's still useful as an intermediary format. It is binary, so it's not human readable. because it offers a lot of the same optimizations that Parquet offers, but it is row-based, so it's more useful for writing heavy workloads such as streaming, or when you want to work with records and such. So here we are at the end of the presentation, nicely on time.